Hello, this is part 2 of my Procedural World Generator tutorial series. In this video, I'm going to go through all the code for each step of the world generation process, and finally finish with setting up a clip map with collisions so we can finally explore our game world with a simple player controller. So let's get started. First, I have this script called World Gen Process, and we set the class name to World Gen Process, and we add in a signal called process complete. So the idea is I'll have every script for each step of the world gen process inherit from this world gen process class, so that when it is done saving the image, we can emit this process complete signal so we know that we can move on to the next step. And then I also start off with having this one class called world configuration, where I set parameters for world generation that the entire project will use during the process, which includes texture size, continent amplitude, which I use for generating my initial landmass image, and then the island amplitude, and then this tile count I use for tiling later on. We have our sea level, world size. I don't use all of these, but I use most of them. This way, all my world generation parameters can be controlled in one place. So the first step of our world generation system is what we call our Landmass Generator. This is how the scene is set up. So I have a margin container and a color rect with our shader, just so that I can see the image within the scene. But this sub viewport and this color rect are what actually get saved. And in order to save this image using the sub viewport, our render target for our sub viewport has to be set to update mode always. As for the shader, we can play with our fall off gradients. We can play with our amplitudes, but these get set in the script from our world configuration script. And then we got some noise textures for continent and islands, and then our fall off gradients that we could play with if we wanted to. So let's take a look at the shader. So here we have all our sampler 2Ds. Set some constants for the distortion that we apply to our fall off gradient right here. And we have our amplitude. Start down here in the fragment function. We get our continent texture space by sampling the continent fall off gradient and subtracting it from 1 so that we get black with white in the middle. And then we pass it through this evaluate function, which is a function that modifies the gradient curve a little bit. I think I got this from a Sebastian Log video. I could be wrong, but I'll link his channel right here. And then we get our actual continent noise value. We have our inner and outer island fall off gradients, and we just use the continent noise to distort the gradient. And this is how we get the direction in which to distort the noise. And you can see we kind of have it distorted radially from the center. And this is how we calculate our actual distortion offset. And then here we apply the distortion offset and return the distorted UV coordinate. And we pass the distorted UV coordinate into the texture function instead of just the UV variable. Then we get our island noise value, and then we get a mask for where our island will go by combining those two fall off gradients. And then here we set the color by multiplying the mask by the noise value and then by the island amplitude. Then we use addition to add the same thing with our continent. That results in this image. Then let's just take a look at our script. So here we inherit from our world gen process, so we get that process complete signal, set up our world configuration, reference our viewport and color rects, get our texture size from our world configuration, an empty variable to store our actual texture when it's ready, and then another one for our material. And this is how we get our references to our gradients and noise textures that we have saved as resources that we load later in the ready function. Set the size of our viewport to our texture size. Then we're going to initialize our landmass shader. So we set the material to our color rect material. And then since we have all these saved textures and gradients, we set them to our shader here. Here we set our island and continent amplitudes from our world configuration. And then this is how we get access to the noise function parameters so that we can change them. We want to make sure the texture size of the noise textures are the same as our viewport. And then to randomize our world, we set the seed of our noise to a random integer. And then we set the frequency of the noise from our world configuration. Back up here, we get our texture from the viewport using viewport.getTexture. But when we do this, we won't be able to do anything with the texture until the texture is available. This function, getTexture, runs on a different thread. So if you try to use the texture immediately after calling this function, it won't be available unless you use an await statement and wait for the rendering server.framePostDraw signal. After that, your texture will be available to use. So then we call the generate landmass map function, where we just call getImage from our texture to get the image. Make a new image texture by doing imageTexture.create from image, set the path, and then resourceSaver.save. Then we give ourselves a little print statement, and then when everything is said and done, we emit the process complete signal from our world_gen process class. So let's run this scene just to see what the output is. Alright, and our process is complete. And if I go into the folder, there we have our saved image. So on to the next step. Now that we have our initial height map, we want to start working on our customization. So the next step is generating a Faultline Mask, which we will use to overlay mountain hills textures onto our initial height map. So here's an example of what I mean. This is our Faultline gradient that we use to overlay our mountain and rolling hills textures onto our previous height map we made. Our scene here is set up the same way. Let's play around with these uniform variables. You can see we separated our uniform variables into fault curve 1 and fault curve 2. You can add more fault lines if you want, but I thought 2 was enough. Center just tells us where the curve is on the y-axis. Gradient offset increases the wideness of the fault space if you wanted fault lines to be bigger. Gradient scale just increases the intensity of the gradient, and then distortion clearly just distorts it. Here are the two curves without distortion. And then UV rotation lets you rotate them around, and curve factor is the actual curve of the line. Now to the shader. Here we have our uniform variables. We have our rotate UV function that lets us literally rotate our UV coordinates at a given angle. We have our warp UV, which is basically the distortion of each gradient. This is our gradient function, which creates the gradient without the distortion. Then down here, we subtract 0.5 from the UV so that everything is centered. Then we have our first fault line and our second fault line. We call the gradient function, and then warp the UV using all our uniform variables. This way you could add more faults if you want to. And then we just combine them using max. Then in the script, start up the same way, load our noise, set the viewport size, initialize shader. When we initialize the shader, we set random values for the center point, the curve factor, and the rotation value of each fault, so that each fault is completely randomized. Then everything else is the same. So once we have our Faultline Mask, we can use it to overlay the hills and mountain textures onto our height map. Here we do this by making a landmass faultline composite that looks like this. So we have our rolling hills texture that tapers off into our more extreme mountain texture based on this fault line gradient overlaid onto our initial landmass map. Pretty neat. How do we do this in the shader? We simply get our landmass map our fault line map. Then we get our mountain range texture, our rolling hills texture. And then we need an amplitude for our mountains and an amplitude for our hills. And then we have threshold and blend radius variables to affect how the textures taper off into each other. We get our landmass and fault line texture values. We get our mountain and hills texture values multiplied by their amplitudes. Then we make a mask for the mountain range and the hills. And then we make a composite of all of these by taking our landmass, adding on top of it our rolling hills value multiplied by the rolling hills mask, plus the mountain range texture times the mountain range mask. Okay, so next we're going to move on to our biome generation, which starts with our humidity and rainfall maps. These are used to calculate our biomes for our biome generator. Starting with the humidity map, it's just a noise texture, and then the shader is just us using the noise for color. And the same goes for our rainfall map, which is pretty much the same thing. In the script, just like before, you can set the seed of the noise to a random integer to randomize the humidity and rainfall maps to get completely random biomes. So now let's go to our biome generator. This might be a little confusing if you haven't already seen my video on how I designed this biome generator. Today I'm just going to show you the modifications I've made to it to generate new kinds of masks for our world generator, as well as adding in altitude-based biomes. So first things first, you can see that we've added some more sub-viewports. This is just to account for the extra altitude biomes, as well as the lake depth mask, swamp mask, and wetland mask that we want for later. And I have another sub-viewport where we just print out the actual biome colors. So again, most of this is explained in my biome generator video, but now we have some altitude-based biomes. Before, where we only used the rainfall and humidity maps to generate our biomes, we now also use altitude. Everything else is the same, but when we made our biome generator before, there were only 8 elements in the arrays for 8 biomes, but now with the altitude biomes there are 13. Here we have arrays for the minimum altitude and max altitude for each biome. And then we have our weights array. Here's where we iterate through each biome, and if the current biome is ocean, we set the ocean weight here so that it doesn't blend onto the land. We don't want our ocean to blend. But then down here, where before we only calculated the weights for the biomes based on rainfall and humidity, now we also use altitude. Then here we've added a few extra parts. Here's where we calculate our lake depth gradient. Here's where we calculate our swamp gradient. Here's where we calculate our wetland gradient. Here's where we set all the biome weights, and then we also save a vector 3 with just the water biomes. And then here we set the color of our color rect based on which biome weight image is set to be displayed. That is controlled from the script. So let's take a look at the script. So here I just put these in so I can set the biome thresholds from the script, as well as the blend radius. Here's where we load our rainfall map, humidity map, and our height map. And here I have arrays for the textures, the color recs, and the materials, just to make it easier with the amount of sub viewports I have. So this is for setting the viewport size. This is for setting up our shaders by setting all the shader parameters. And then here we get our viewport textures. And after that, we have to wait for the rendering server .frame post draw signal, and then we can generate all the images we would like. So for each of the textures saved in our textures array, we call getImage, make an image texture, make an empty path. Then we want a path for our water biomes, path for our lake depth mask, swamp masks, wetland masks, biome colors, and then all the other ones are our actual biome weight images that we are going to use. For that, we just call it biome map 0 through 5 or whatever. And then we save each image texture. Okay, so now that we have our biomes, we want to flatten all the water biome regions to the average altitude of all the pixels in that region on the height map. To do this, we need to know which blobs of water biomes are connected to each other and separate from each other. Right now, in our water biomes map, a water biome has a value of 1, everything else has a value of 0. This means that right now, in a per pixel shader, we would only be able to differentiate between water biomes and non-water biomes, rather than differentiating between individual water biome regions, which is what we want. So, in order to know which water biome regions are separate from each other, we can use a flood fill algorithm to assign a random color to each individual region. Then, with a similar flood fill operation, for each region with a unique color, we average the height of every pixel in that region and set the height of each pixel in that region to that average height. The flood fill algorithm is the same type of algorithm that the bucket fill tool in most paint programs uses. It's also used in Minesweeper. A flood fill algorithm can be designed to be recursive or stack-based. A recursive flood fill algorithm would just use GDScript's call stack to handle the recursion, which can lead to memory leaks and stack overflow if there are any errors. And when I say GDScript's call stack, I'm talking about the internal stack GDScript uses to keep track of function calls and where to return once each one finishes. So for this, we are going to use a stack-based flood fill algorithm, meaning we will explicitly define and manage a stack or queue of all the pixels to be filled. So here I have a scene called Water Biomes with Unique Colors. You can see that this scene is just a Node 2D with a script. So this script is my first flood fill operation that will produce an image called Water Biomes with Unique Colors. It takes our water biome mask as an input image and returns an image where all the water biome regions are filled with a unique and random color. So down in the ready function here, we load our lake mask and get it as an image. And then we call a function called floodFillLakes. I meant water biome mask, but I called it lake in this. Who cares? So in our floodFillLakes function, we create a new output image. And we copy all the data from our lake mask. This is mostly to get it to be the same size. Then we get our height and width. Make an empty dictionary of all the pixels we've already visited in our flood fill. Now we just loop through each pixel of the lake mask. There we want to get the pixel color for that pixel of our lake mask. And then I set it to a vector 3 instead of a color type so that we can use comparison. So here, if the pixel color is not black, and it is not in our dictionary of visited pixels, then we will generate a random color and then perform the flood fill to color that region. So basically, anytime our algorithm finds a non-black pixel, it will make a random color and fill the connected region with that color. So let's take a look at this generate random color function. So we have this empty array called used colors for keeping track of previously used colors. We have an empty new color. And then we have a Boolean variable called isUnique that is set to false by default. Then we'll just do a while loop. If not isUnique, then generate a new color. And then once we have a new color, isUnique is equal to true. And then we just have to check to see if the color has already been used. And if it has been, we set isUnique to false. And then we add the color to used colors and return the color. So then we arrive at this flood fill region function. Let's take a look at that. It takes our output image that we are going to modify, the input image, the X and Y coordinates of the pixel, our randomly generated color, and then our dictionary of visited pixels. So this is the main flood fill part of our algorithm. We start with an empty stack array. We add our starting pixel or seed pixel coordinates to the stack, and while the stack size is greater than 0, then we just get our current pixel from the array with stack.popback, which basically removes and returns that element from the array. Then we just separate our X and Y components. Then we get the pixel color of the lake mask at those coordinates, convert it to a vector 3 again, and if this pixel is already in visited pixels, or if the pixel color is black, we just skip this pixel and go to whatever is next in the stack. So if that pixel is part of a lake, we mark the pixel as visited, and then we set that pixel of our output image to our fill color. And then the next step is adding the pixels above, below, to the left, and to the right of that pixel to our stack, so that our function can recursively perform this flood fill operation. So this function modifies our output image, so then we want to make an image texture from that output image and save it. So now, if this is the water biome image that we have saved from the last step, if we run this script, let's see what it does. Okay, it saved our water biome's unique colors. And let's take a look. Here you can see that each water biome region has its own unique color. Some of the colors look very similar, but they have very minute differences in their values, so they are technically unique colors as far as our algorithm is concerned. So now that we have our water biomes with unique colors, we want to essentially iterate through each unique color found on the image and average the heights of our height map within those regions, and then we set the color of each pixel in that region to that average height. So we're going to do this using another flood fill operation. For this, I just have a scene I called water biome level, and it works very similar to the last script. It takes our water biome image, and then our most recent height map, and then an empty variable for the output image to be saved to. Here I just have a main function. So here we have an image with all our average heights using this calculate average height function. And then we go ahead and save the image data, and then we emit our process complete signal. So the calculate average height function, do the same thing as last time by initializing our output image, get our height and width. Here, instead of tracking our visited pixels, we track the entire regions that have been processed based on the color of each region. Then we iterate through height and width, get our water biome pixel color. If this color is found in our processed regions or the color is black, we skip. Otherwise, we collect all the pixels in the region with that water biome color. And then we have to calculate the average height for the region, so we start by setting total height to 0. Then for each pixel in our region pixels, we add the height of that pixel to our total height. And then to get our average height, we divide total height by the amount of region pixels we have. And then we assign the average height to all the region's pixels in the output image by looping through the pixels and doing output image.setPixel. And then we mark this region as processed and return the output image. As for this flood fill region function, down here, we have our output image, our input image, the starting pixel coordinates, and the region color. We have an empty array for pixels and then our stack array. And we do the same thing as last time by adding the current pixel to the stack. And we get our height and width. While stack size is greater than 0, do the same thing as last time. Get our pixel color for the image. If the pixel color is the same as the region color, then we add that pixel 2 pixels. And then we set that pixel of our image to black so that our algorithm sees it as being already visited. And then we just add the neighboring pixels to the stack and we return pixels. And then lastly, we save the image data by making an image texture and doing resource saver.save. And then in the ready function, we just load the water biomes with unique colors image and the height map image, and then we call our main function. So let's run it just to see how it looks. Alright, let's just look at the image it created. Alright, looks pretty good. You can see the average altitudes for each water biome region. So now that we have the heights for each water biome, our next step is to flatten each water biome on our height map using these altitude values. So here I have a scene called Landmass Flat Water Biomes. If I zoom in on the water biome regions, you can see that it is flat and it is an average of the heights of all those regions. Scene is set up the same way. Let's take a look at the shader. Okay, so we have our height map and then our original water biome mask over here. And then we have our water biome altitudes. And we use the filter nearest hint because otherwise it uses the linear interpolation filter by default. And you can see if we do that, we get these weird outlines around our flattened water biome regions, which is not what we want. The best and easiest solution for this is just to use the filter nearest. That way we get the exact correct values for each pixel. So down here we get our values for our height map, our wetlands, our swamp, and then our lakes. And we get our altitude for each water biome region. Make a water biome mask by adding them together and then clamping between 0 and 1. Then we use linear interpolation with our mix function here to make a composite of all the data. And then this line right here I actually don't need. I don't even remember what that was for. So that's how we get our flattened water biomes. But now we need to apply our water biome textures to these flattened regions. So here I am in my next scene, which I have called water biome textures. Some values need to be adjusted to make it look better, but I made them more extreme so you could definitely see that here we have a lake with a depth gradient, and then here we have a wetland or swamp with a super high frequency noise texture. Again, right now we're using a single image for our entire world map, so later when we use tiling, we'll get a much better texture resolution here. So here we are in the shader. We have some uniforms for scaling the height values how we would like. Sampler 2Ds for the wetland mask, swamp mask, and lake depth mask, and then our height map. And then we have a swamp noise texture and a wetland noise texture. Here we get our original height, then we get our lake depth, our swamp height, our wetland height. Then we sample our swamp and wetland textures. Normally the texture color values are between 0 and 1, but since we want the swamp terrain texture to go above and below the water, we do this thing here where we multiply it by 2 and then subtract 1 which remaps any values between 0 and 1 to be between -1 and 1. And then we multiply that value by our swamp scale and wetland scale. Let me fix that. Then we make a mask by taking our lake depth value, adding onto it our swamp mask with our swamp texture, and then our wetland mask with our wetland texture. And then here we basically overlay those values onto our height map. So this is basically our finished height map that we're going to use in our game world. So now that we have our final height map, I want to make a scene called Game World. That'll be our main scene where we see our finished world. I went ahead and made this quick clip map in Blender. If you want to know how I made this, I just made another video on this, linked here. Here we have the clip map saved to a scene with the mesh instance itself as the scene root. Now I want to apply a clip map shader to this clip map. I'll add a new shader material. So I've already made a shader. We'll get into how it works, but let's add our height map. As well as our biome colors image. You can see if we drag the plane around, our actual world map is tied to the world coordinates. So first we have our two sampler 2Ds, our tile size in world coordinates, and our amplitude, and we get these from the world configuration file by setting these parameters in our clipmap script. Then I just have a varying vector 3 for the world vertex, so I can use it in the vertex function as well as the fragment function. In the vertex function, first we get our world coordinates by multiplying the model matrix by a vector 4 with the vertex coordinates and with 1.0 as the W value. And then of course we just take the X, Y, and Z coordinates. Next we get our texture position used for sampling the height map and the biome colors image at the correct UV coordinate according to that vertex's world coordinate. We do this by taking the world vertex coordinate and then add to it 1/2 of the tile size. This makes it so our world is centered rather than starting at 0 and going off in any direction. The reason we add 0.5 here is, like I said earlier, when we add collisions later, in the shader the image gets sampled at the corner of each pixel, while in GDScript it gets sampled in the center. So in the shader we add 0.5 to sample the center. And then to get our final height, we start by setting an empty height variable. And then here we have an if statement that basically says if the world is within our world bounds, set the height to the height map texture. Otherwise, leave height as 0. The reason I subtract 0.5 here and here is specifically because I add it up here. Otherwise, the edges of the world on those axes would start to wrap and sample the repeated image right on the border. And then we set the vertex.y to the height times amplitude. In the fragment function, we do the same exact thing and just set the color to our biome colors image and then set the albedo to color. Now we want to have a script for our clip map. Here's the script I have made already. We want a reference to our player for when we start setting up the game world. We want our world configuration file so we can use the values from that. Here we have a terrain snap factor. You can see when I drag around the clip map plane, there's a weird wobbling effect at the lower resolutions. This is because we want to snap our clip map to only move at certain intervals so that our vertices always line up with the right pixel to be sampled. Here in the ready function, we just initialize our shader by setting the height map texture size and the amplitude from the world configuration. Then in the process function, we set the global position of the clipmap plane to the player's global position and snap it at every terrain snap factor interval, set in a vector 3. Alright, so that's the basis of our clipmap. I have this little player scene that's just a camera and a capsule collider with a little player controller script. So I'll have a new 3D scene we're going to call Game World. I'll add my player to the scene. Then I'll add my clipmap. I'll move my player up on the y-axis so he's above the ground. And then I want to assign our player in the clipmap script. Let me just add an environment and a sun to the scene. Now let's try running the scene. So as I fly around, you can see that my clipmap follows me around and snaps, and there's no wobbling effect. So now that my clipmap works, we need to have collision so that we can run around on the ground. So here I have a new scene called Clipmap Collision, which is just a collision shape 3D, and for the shape I've set it to a concave polygon shape 3D. And then we have a Clipmap Collision script, which has an export variable for the player, and then another for the template mesh, which we can assign right here. We'll choose plane mesh, and that's our collision shape. We want to make the size something a lot bigger, like 30, and we want to subdivide it so that all the vertices lie exactly on the same vertices as our clipmap. So we do that by basically taking the size and then subtracting 1. So 29 subdivisions. Let's take a look at the script. So again, this collision script is heavily inspired by DitzyNinja's Clipmap and Collisions video, linked again right here. So here we have our export variables. Then we get each face of the template mesh so that we can iterate through them later. And then we take our height map image and do get image. Then we have our world configuration, our amplitude, and then for our terrain snap factor, since our collisions will always exist in the LOD 0 region, we can basically just set this to be any multiple of 2 and it'll snap perfectly. So in the ready function, we start by immediately calling an update collision shape function. We basically iterate through our faces. Then we get the vertex associated with each face. And then we get the global position of the vertex by taking the vertex position and adding the collision shape's global position to it. Then we get our global texture coordinate the same way we did in the shader by taking our global vertex and then adding on half of the texture size in the form of a vector 3. And then we set the height of each vertex using this getHeight function, using the global texture coordinates. And then once the for loop is done, we update the shape by using shape.setFaces. Let's look at this getHeight function. All we do is take the x and z coordinates and sample the height map at those coordinates and multiply it by our amplitude. So now back in our game world, I'll just add a static body 3D. And then I'll just add our collider scene as a child to it. And assign the player. And I'm actually going to set the color of our clip map to a dark grayscale so we can easily see the collider. Let's run the game world. Alright, looks pretty good. So you can see here If I remove the 0.5 that gets added to the world vertex, our collider won't completely match up with our clipmap terrain. Cool, so our collision matches up perfectly with our world. So this is the base of our world generation system. We used several shaders and sub-viewports to process images using these shaders to generate a height map as well as biome maps for our world. Then we use a basic clip map and terrain collider as our game world. So, in the next video, I'll show you how we can implement a simple tiling system to this world generation system so we can increase the size and detail of our world terrain to our liking. If you would like to support this work and help me make more of it, feel free to buy me a coffee on ko-fi.com. And if you wanted to support me further, I now have a Patreon where I will be releasing videos early before they appear on YouTube. Thanks for watching.